Oh, someone went back to Roblox. Are you ready, Thomas? Let me know when you're ready, Thomas, and you're recording, and we'll start.
I'm recording.
Oh, you're recording? Cool. Give me 1 second. Let me pull up all of these Leetcode problems on my iPad as well. So we were doing. Oh yeah, first we have to do binary search. All right, did y'all watch that video I posted on binary search? The 2CS60 video? Anyone here not read it or watch it? I'll be disappointed if you didn't watch it, because those videos are insanely good. All right, pull this up. 1 second, guys. Almost done setting up my iPad. Cool. All right. Thinks we're good to go. Let me share my screen. Share everything. All right, hop on to the video chat when you guys are here. I'll give you all like 10 seconds to hop in, and we'll get started. Leetcode Friday number 3, guys. We're getting there. We're getting there. I hear you guys still joining. Give you like 10 more seconds to join. I'm sharing my screen. We're gonna do some binary search, the best algorithm of all time. All right, let's get started. All right, so we are doing binary search today. Binary search is going to be this is probably one of the best algorithms to start with whenever you're learning how to create an algorithm and how to write them, just because it's so intuitive. So you guys hopefully saw the video, but I'm gonna just quickly just explain again just a little bit of how it works. All right, so here we go. So here's the list that we have over here in Leetcode. So say you want to find the number 9, right? Right? What you could do is you could just read through this list one by one. All right? Is this 9? No. Is this 9? No. Is this 9? No. Is this 9? No. This is 9? Yes. All right? This is where you're linearly searching through the array. It's called linear search. I'll write it down. This is called linear search. The way you would do this is you do something like something like I equals 0 to n being the size, right? This is just pseudocode. I plus plus, right? And then you just say if whatever nums, whatever I equals target, return I. Something like this. This is called linear search. You're literally searching through this just one by one, no methodology involved. Now, this is all cool and easy if you have just a small little array. But if you have, say, an array of like 10,000 items, what if you're looking for the item and it just happens to be the last thing of the array? And that means you have to search 10,000 times. So if you have 10,000 items, you're searching 10,000 times. This means that the time complexity is linear. It's in the names, linear search, linear, which would be big O of n, with n being the size of the array. This is pretty crappy because it takes a long time and it's just going to scale exponentially. If you watch the CS50 video, it's like 1 minute long, so I hope you did. David Malin goes over a phone book, right? You're trying to find someone's number in a phone book. I think you guys might be too young for that, but phone books are a list of numbers from businesses and people back in like 2000, where you had just a big list of people, their phone numbers, maybe their addresses, public information. So say you wanted to find like, I don't know, Louis Pizza's number, and Louis Pizza, you don't have their number on you. So you have a phone book, it should have it somewhere there. Now, how are you going to search for Louis Pizza? Are you going to be going through this giant book and just like page by page search through that book? That's like those phone books are friggin' huge. They're like 1,000 pages sometimes. So good luck trying to find Louis Pizza searching through a phone book with 1,000 pages. It's going to be thousands and thousands of phone numbers. It's going to take you absolutely forever. So instead, we can kind of optimize that. A phone book is technically sorted, right? This is the key. If something is sorted, then, for example, A's are going to be first, and then Z is last. So we can use that to our advantage. We can think, all right, we have this phone book. What if is let's look at the middle. What's the middle of the alphabet? I don't know. A B C D H I J K. I don't know. Like say P or something. I'm just kind of guessing, right? Let's say that N is the middle of the alphabet. Someone can probably fact check me and let me know. I'm just kind of making this up right now. All right. We're looking for Louis Pizza. Is L before or after N? So it's A B C D E F G H I J K L M N O P. So it's before. So Louis Pizza is somewhere in here. So we don't need to check anything between N and Z. There's no point. So we can just cross that out right now. And that just saved us half of the entire phone book. We just ripped the problem in half. All right, now let's keep going. We got Louis Pizza, and now N is the end of our array. And somewhere here is Louis Pizza. Because I want some pizza right now, even though it's like 7 p.m. All right, now let's find the midpoint. A, B, C, D, E, F, G, H, I, J, K, L, M, N. So it's 14 letters. A, B, C, D, E, F, G. So G would be the midpoint. All right? What's in between A and... So now we're going to check. Is Louis or L here? Or is L after the midpoint? All right? So A, B, C, D, E, F, G. L is not here. We can cut the problem again in half. L is somewhere in here. And then we can go A, G, H should be H. And then N, we're just going to go one up. And then we're going to find Louis. Is he here? H, I, J, K, L, M, N. Well, it's in between that. So, but is it H? Find the midpoint. H, I, J, K, L. I'm just going to say it's K just for fun. All right, here's the midpoint. Is L here? No, it's not. Let's cut this in half again. And then K to N, L, repeat the process. Eventually, we're going to find L. All right, this is what binary search really is. You're going to cut the problem in half, and you're going to compare if it's in the left half or in the right half. And then you're going to search that. This means that you're cutting the problem in half means it's logarithmic. So if you think of like a graph and say the higher up on the y-axis is say, let's say that's number of items, right? And then say the x-axis is time to find search, right? That means that by cutting the problem in half each time, if you have a billion numbers you're searching through, you immediately you're already cutting off 500 million. Then you only have 250 million, 127.5 million, and it just cuts down really, really quickly. So your graph is going to look like something like this. All right, this is going to be log base 2 of n, because we always do base 2 in terms of big O. So that means if you have like 1 billion, it might only take like 30 steps. I know just out of the top of my head, 1 million is 20 steps. So 1 million items, just searching a million items to find a number is just 20 steps. It's actually a really fun game if you want to like place bets with someone and be like, hey, I bet I can guess what number you're thinking of between 0 and a million. I can guess it in 20 steps. I'll bet you $500 I can guess in 20 steps. You're going to be pretty rich if you realize this algorithm. So let's kind of talk about it and just kind of pseudocode it out. And every single one of these problems is going to be based off binary search. So you're going to be just applying binary search in every single way, slightly different, tweaking it a little bit, but it's pretty much the same concept. So hopefully, once you understand this concept, you should be good with any binary search problem. And this is going to be a really good algorithm to learn because you're learning about being more efficient, and it's really easy to write. All right, so how do we think of this? Let's think of it more step by step. All right, so let's say we have an array, right, from 0 to 1000. Okay, we're going to say that low is equal to 0, which is the low point, right? High is equal to 1000. Okay, we're searching between 0 and 1000 inclusive, so it's going to be low as 0, high as 1000, right? once we have that, we want to make sure that they don't ever overlap. These are technically two different pointers. We have a low pointer and a high pointer. All right. So while our low pointer is less than or equal to our high pointer, aka they don't ever overlap, we're still searching. It's still like we're still looking through the array, because once they overlap, then we've already searched the entire array. We can stop. All right. Let's find the midpoint. So the middle is going to be just high plus low, right? And we're gonna divide it by 2. I'll make it even cleaner. High plus low divided by 2. All right, and then rounded down. So for example, if that means that, example, if you have 9.5, then we're just gonna round that down to 9, just because we can't index into an array at 9.5. So this becomes 9. Okay, so what we've done is we've gotten our phone book, we found the midpoint, okay? So all we've done so far is set our low and our high pointer. We found out the first letter of the phone book and the last letter Z of the phone book. We found the middle letter, the midpoint of this array. All right, now that we've done that, let's do some comparisons. Let's say if, let's call us, I don't know, nums, because we always do nums. Nums mid. So we're just indexing into the midpoint of the array, right? Because if array is from 0 to 1000, we have, and say it's just 0, 1, 2, 3, 4, 5, this is the length, right? Clarify that. Length equals 1000. So if numbers mid equals our target, that means just return it. Return this index. Because over here it says given an array your answer, it's your target. Target exists, return its index, or otherwise return -1. So I'm just returning the index. So for example, over here, in this array, 1, 2, up to 9, target is 9, the index is 4, because 0, 1, 2, 3, 4. Just so you guys are on the same boat, right? We're returning an index. So let's do some comparisons. If this midpoint is greater than the target, that means that the target, so here's the midpoint, right? Here's mid. Say mid is over here. If this is greater than the target, that means search the left side of the array. So you can actually do this in 2 different ways. You can do this recursively, which kind of makes sense. And I'm going to write just recursively for now, and then we can do it also iteratively. So you can say if the number is in the left and the mid is greater than the target, then the target is somewhere in the left half of the array. So we're going to search that. Else, it's somewhere in the right. So let's search it. Search the right half. And then just return -1 at the end if nothing else happens, right? So this is the entire algorithm, right? While low is less than high, less than equal to high, you find the midpoint, round it down. If the number we're searching for in the array is equal to the target, just return that index. Or else if the number is greater than the target, it's in the left half, so we're going to search the left half of the array, or else we're going to search the right half. So this is just a very intuitive understanding of it. I'm going to show you the recursive form first, and then I'm going to show you the iterative form next. So let me just set up my Leetcode. Quickly stop sharing my screen. Let me delete this. Okay, cool. All right, so let's do that right now. Make sure I'm sharing my screen properly, right? Yep, we are. Cool. All right, so let's try this the recursive way first. Right? We have to make a helper function, call it binary search. And we're going to just take in the same list numbers, target, low, and high. And this is in Python, by the way, but I'll show you some C stuff as well. So just to practice recursion, here's our base case, right? If low exceeds high, the target doesn't exist. So you can say if low is greater than high, return -1. And let's find the midpoint. Mid equals low plus high divided by 2. In Python, if you do double slash, that just rounds it down using integer division. That's just a Python thing, but you can do something like int low plus high divided by 2, something like this as well. All right. Now, if the middle element is the target, so if nums mid is equal to target, return mid. Easy. We found it. If the target is less than the middle element, search the left half. Right? So that's just else if nums mid is greater than target, return binary search. So we're doing the recursive call now. Nums target low mid -1. So all we're doing is we're putting in nums and target. This is the same as the original array. Our low is the same, and since the number we found in the middle is greater than target, that means it has to be at the left of the array. So the high will become mid -1. So we're turning high into mid -1. So we're cutting off the right half of the array. And then else return binary search nums target, and then mid +1 high. So what we're doing is over here, if the target is greater than the middle element, search the right half of the array.
May I ask a question?
Yes.
Where will this code be posted?
Yeah, sure. I'll post it.
Or like you said, there was like a video somewhere.
I sent a video of the pseudocode, but I can share this code afterwards as well.
Okay, where would I be able to find the video?
We're gonna of this lecture.
Yeah, or just
It's gonna be on the Code for All YouTube channel, but I posted on Discord in the announcements. Like it was right here. Watch these 2 videos on binary search if you don't know what binary search is. It's in the announcements.
Oh, but like I meant like you going over the code and stuff.
Oh yeah, I'm gonna share it. We're gonna upload that later on.
Okay.
Yeah. Okay. Cool. All right. Anyways, so what were we saying? So we did our base case, right? If the middle element is the target, which is kind of like the base case as well, then we're gonna return that mid. If the target is less than the middle element, search the left half. If the target is greater than the middle element, search the right half. And then we're just gonna return this. So return binary search nums target, and then just 0, and then length of numbers -1. So what we're doing is all of this stuff, right, is only run at the end. So we only have one line of code in this entire search worker. We're just running this. We're starting with the array numbers, the target. Our low is 0. Our highest length of numbers -1 because arrays are 0 index. So if we run it, it works. This is binary search. Do you have any questions on the recursive method of binary search? Any questions at all? Again, this is a recursive method just so you guys can get some practice on recursion. Nope. Okay, so then I'm going to show you the iterative way next. All right. So this was the recursive method. I'm going to copy this and just paste it into Leetcode so you guys can see this. It's good to understand recursion and to use recursion just to practice, but it's actually less efficient. So here we go. Python binary search recursive. All right, so this binary search, again, we talked about was big O of log n, right? Because it's cutting the problem in half. And unfortunately, since we're using recursion, this actually takes up space. So space complexity, I believe, is big O of log n as well, if I'm not mistaken. So space complexity is log n because every single time that we call binary search, we're adding one call to the call stack. So you're going to learn about the call stack later on in some of your other classes. But technically, each time we call a binary search in recursion, you're adding something to the stack. So you technically are using memory. So it's not the most efficient way in terms of memory efficiency, but it's just good to know this is recursion. All right. All right, let's go to the non-recursive method now. And again, I shared this into the Leetcode channel. All right, so let's do binary search again. Except let's do it the iterative way. So iterative way. All right, so low, high, right, equals 0, length of numbers minus 1. So again, length of numbers minus 1 is high because arrays are a 0 index. So length, so if length is 100, 99 is highest index. Right, that's why we're using minus 1 to the high. Okay, next. If low is, sorry, whoopsie. While low is equal to, less or equal to high. And again, this is just copy and paste pretty much. Mid equals low plus high, integer divided by 2. If numbers mid is equal to, oopsie, is equal to target, return mid. That's just saying if the middle number is a target, return its index, right? Else if number is mid, so the midpoint is greater than the target, then like I said before, you're going to search the left half of the array. The way you can do that is by saying high equals mid minus 1. So you're making the high point. So say if this is the array, right? And say it's, yeah, negative 1, 0, 3, 5, 9, 12, right? This is your array. We're looking for 9. Let's say target is negative 1, just for this example, right? Then this is the midpoint. I just divided over here. And this is technically the mid number. It's less, so we're going to search this half of the array, specifically just these two. That's what we're doing. Or an else is the opposite, so just be low equals mid plus 1. And by saying that, say target is 9, right? This is the midpoint. And then 3 is the number that we're checking because we're rounding down. So 9 is bigger than 3, so we're going to check this half of the array and cut this half. So the midpoint is going to become 5 next. So mid is 5 now. Sorry, the low is 5 and the high is still 12. And then technically it'd be the second mid is right there, so that's the target. All right. And then that's it. Just return -1 if you don't find it. Submit that, and there you go. So this is time complexity is log n. Space is actually O of 1 because you're not using any additional memory. So technically the iterative way of doing binary search is better, but it's good to understand how it works both recursively and iteratively. All right. And now, just for fun, because you should be doing this for every single language so you understand these very on a fundamental level. Let me just delete this. All right. Let's do some binary search in C. Why not? Again, you do a low equals 0. You do a high, and I'm going to show you something funny. This is the same thing in every language. So you do size of numbers -1, right? Same as before, while low is less than or equal to high. Your midpoint is equal to low plus high divided by 2. I hate the if your midpoint numbers, right, is equal to the target, then just return the midpoint. Else if the midpoint is greater than target, then again high is equal to mid -1. So we're just searching the left half of the array. Else then just low equals mid plus 1. And then if you can't find it, return -1. And if you run it, oh, I hate this language so much. If you run it, oh my god, I hate this language. Run it. Did I forget a parenthesis or something? Time exceeded. What did I forget? 1, 2. What did I do? +1, return -1. I'm just going to go to what I did before because I don't know what was my mistake. C++. I have no clue what was the difference. this thing is dumb. All right. So yeah, here we go. Binary search is done. This is C++. It is done. All right. And just for fun, let's show you how to do this in like every other language. So here's C++. And this will only take 2 seconds because it's so easy. All right, let's do Java. Same thing, look. Same exact thing. All I did was I changed the length without the parentheses. Look, Java, C++. Java, C++. Java, same exact thing. If you want to do it in C, same thing. Int low, int high, same exact thing. And this also works. If you want to do it in JavaScript, same thing. Run it. Same exact thing. So once you learn how to apply this algorithm, it's practically the same thing in every language. And just for fun, I'll show you the code in C++ because I know lots of you guys are in 111 if you're doing this problem. So here we go. C++, binary search. Here we go. All right. Any questions on binary search? No questions at all? All right, let's do the next one. Open this up. Ah, why you open Safari? Okay. Don't look at this. Okay, there we go. Let's share my screen on the iPad. Let's look at this next problem. Let me just pull it up on my iPad. Guess number higher or lower. I'm just taking a screenshot and posting it on my iPad. All right, let me share the screen. And now that we know binary search, we're going to go by this really quick because this is literally the same exact thing. There's nothing really crazy or hard about this. This will take like 2 seconds. All right, this is our next problem. Guess number higher or lower. We're playing the guess game. The game is as follows. I pick a number from 1 to n. You have to guess what number I picked. Every time you guess wrong, I will tell you whether the number I picked is higher or lower than your guess. You can call a predefined API called guess, which returns 3 possible results. -1 if your guess is higher than the number I picked, 1 if your guess is lower than the number I picked, and 0 if your guess is equal to the number I picked. All right, so this is literally the exact same thing as binary search. You just say it's just we're playing a guessing game. All right, so let me just make sure y'all can hear me, right? Just making sure I'm not muted. Is that cool? All right. All right, so here we go. We're playing a guessing game. 1 to n. Our low is going to be 1. High is equal to n because 1 to n. Great. Binary search. Every time you guess wrong, I will tell you whether the number I picked is higher or lower than your guess, and we're going to call it guess. So while low is less than or equal to high, right? Mid is equal to low plus high divided by 2. We just find the midpoint. Let's check the result, right? Result is equal to guess mid. So over here, if you look at over here, it says you can call a predefined API. Guess mids would return the 3 possible results, right? So let's do that. Let's check these results. If result is equal to 0, right? That means your guess is correct. Return. Your guess is correct. You did it. If else if result is equal to -1, that means your guess is higher than the number I picked. So that means your number is greater than the picked number, which means you are going to search the left half of the array. So that's just high equals mid minus 1, or else you're searching the right half of the array, which is just low equals mid plus 1. Easy peasy lemon squeezy. Where this is just binary search in just a fancy name. We're just playing the guessing game. It's from 1 to n. You're calling in the question, the guess API. It tells you -1 if it's on the left side of the array, 1 if it's on the right side of the array, and 0 if it's exactly in the middle of where you're searching, aka your guess is correct. So this is like what I told you, when you play a game with someone, bet them like $50, you can't guess their number between 0 and a million in 20 tries. This is exactly it. All right, let's do this. So, 1 second, let me just, yeah, we're good. All right, so low, high equals 1. I can't spell high. High equals 1, n, while 1, n, while low is equals, let's say, equal to high. Binary search, boys. Mid equals low plus high. Integer divide by 2. Result equals guess mid. So we're just guessing now. So let's guess at the midpoint. If result is equal to 0, return mid. That means that if we are right. Else if result is equal to -1, then that means the answer is on the left side of the array. So we're going to do high equals mid minus 1, or else it's on the right side of the array. Low equals mid plus 1. That should be it. Yay, it works. Okay, we did it. Any questions on this problem? Any questions at all? No? All right, let me get the next one. First, bad version. Let's set up my iPad. So again, all we did was we did binary search. It's very, very much the same exact algorithm, which is really cool that we're doing this because we're going to be building up binary search as we go on. All right, let me share my screen again. All right, 1 second. Well, hold on, I want to just quickly delete this. Don't look, don't look, don't look. Don't look, don't look, don't look. Don't look. Reset, there we go. Cool, okay. All right. Next question. First bad number version. Again, this is if you did 111, but honestly, anyone can do this. If you can do binary search, this is just, again, binary search. So this time, and again, you can see that the question, binary search is just asked in 100 different ways. When in doubt, if it's sorted and you're searching an array, do binary search. All right, you are a product manager and currently leading a team to develop a new product. Unfortunately, the latest version of your product fails the quality check. This sounds like an interesting problem. Since every version is developed based on the previous version, all the versions after a bad version are also bad. Suppose you have n versions, 1 through n, and you want to find out the first bad one, which causes all the following ones to be bad. So your search, so that means that if there's a bad version at index 5, say here's an array, right? And it's like 0, and index, this is just indices, and then this is like n. And say if at 5, this is bad, then that means that everything else is bad. All right, so we're trying to find the first bad element is what they're asking us. Okay, and we're giving an API called bool, which gives a boolean is bad version. and we're going to put in some index, right? And it'll be true if bad, false if not bad. All right. So at first it might be like, all right, what if I just search this array one by one, linear search, and the second that we find a bad version, then return it. That makes perfect sense. But again, this is OFN. That sucks. It's why would you do that to yourself? All right. So no linear search. No good. We're doing binary search. The reason why we can tell it's binary search is because over here it's sorted. It says n versions from 1 to ... n, right? That means it's sorted. If an array is sorted, binary search is the answer. This is a trick. If the array is sorted, binary search is your answer. Let me just drink some water. Cool, so how are we going to do this? All right. Low, high is equal to 1, n. Actually, I don't even need to do to to do the drawing, but we're just gonna do a binary search. Get out of here. All right. Low. Actually, even better. Let me just copy and paste this. Again, this is just how repetitive binary search is. All right. We just copy and paste it from the last problem, and we're gonna have to change a little bit. Okay, so then instead of, let's see, where are we? There we go. Let's say bad is equal to n. So let's say bad is the last number of the array. This is sort of like our base case, right? So there has to be something that's bad. So let's just for now say that the last number of the array is bad. All right, well, low is less equal to high. Midpoint is low plus high divided by 2. All right, instead of if result equals 0, we're going to change this. If is bad version, mid, then we're going to say bad is equal to mid. So what we're saying is that, all right, if the midpoint is bad, we're going to set the worst bad number to be the midpoint. But we're not going to return it because we're going to keep searching. All right? Anyone, was someone saying something? No? Okay. All right, so we're saying if something is bad, then we're going to call that the worst bad version rather than just the last number of the array. And we're going to just change this. So we're going to just delete this whole thing. So once we find that bad version, we're going to just say high equals mid minus 1. So what we're saying is we're going to keep searching now the left half of the array. So we found that the current midpoint is bad. So that means that the first bad version is going to be left of that current bad if there is one. If not, then if it's so, then if we find a good version, so say we're searching through the array over here, and it's 0, 1, 2, 3, and this is the midpoint, and then 4, bad, 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 right? So if this midpoint is good still, then we're going to make this the low number, and we're going to search this half of the array. All right, we run it. Oh, oopsie, I forgot to return something. And also, this doesn't exist. We don't have to guess anymore. Return bad. Oh my god, I'm screaming it out. Return bad. Yay, we did it. All right, as you can tell, if you look at this, right? It's the same exact thing. We just change a couple different like words. And in binary search, the exact same thing. All right, does anyone have any questions so far? We literally just applied the same exact algorithm to 3 different problems. Any questions on these easy Leetcodes? Any questions at all? Nope. Okay, then we're going to move on. Let me just delete all of these so you can't see them. All right, reset my answers. Okay, so now that you guys probably have done binary search a bajillion times and you just kind of understand it, let's do something a little bit more interesting. So we're not just going to be applying binary search and just returning that and just solving a LeetCode. That you're not going to get that in an interview. That's just basic 211 stuff. So let me just get the question on my iPad first and last. Position of element in array. Yep, search range. Let me take a screenshot. 1 second. All right, let me paste it to my iPad. Let's do some LeetCode mediums. Okay, let's share my screen. All right, this time, this is our first medium problem. Find the first and last position of element in sorted array. Given an array of integer nums sorted in non-decreasing order, that means if it's non-decreasing order, it's going to be something like this, like 0, 1, 1, 2, 2, 3, 4. This is non-decreasing because that means you can have duplicates. That's all it's saying, non-decreasing order. So given an array sorted in non-decreasing order, find the starting and ending position of a given target value. If the target is not found in the array, return -1, -1. You must write an algorithm with O of log n complexity. This part right here, log n complexity. What search algorithm is log n? What's the only search algorithm of log n? Binary search. This is how you know you're supposed to do binary search. So, an easy brute force way of doing this is that you can just do linear search, right? You can search through array, right? Say it's 5, 7, 7, 8, 8, 10, and then you can set low, high, so equal -1 or something, so it doesn't exist, right? And then the second you go through the array each time, right? Or we're trying to find target is 8, right? And then once you find the first one, then low equals 3 because 0, 1, 2, 3, right? We keep searching and we found the last version of 8. This is high, so then high equals 4. So we return 3, 4. That's the first output over here, right? You could do that. That's not log n though. So if you're at like Google or something and they're interviewing you, they're gonna look at you like you're dumb. Don't do that. But this is a brute force way of doing searching for solving this answer. But we're smarter than that. We know that why do you search through something that could be a million steps in a million steps when you can just do in log n time by just doing binary search because it's sorted. So here is my first solution. So I actually came up with a more naive solution. And it technically was log n plus that could go all the way to n. I'll show you what I mean. But this is sort of like a more brute forcing naive, but still not a perfect method. So what we did was let's do binary search. I'm not going to write it out this time because you've already seen it so many times. So binary search, right? Once we find the target, right? Once we find a target, search left linearly until the first version, until first instance, and then search right as well for last. What that means was this is the more naive way of doing this would be say you have an array and it's let's do something a little bit longer. So 2, 3, 4, 5, 5, 5, 5, 5, 6, 7, 8, 9. Okay? Here's your array. And we're gonna do binary search on it. So we find the midpoint. I'm just gonna guess it's around here, right? And say target is 5. Okay? So what we could do then is, all right, we found a target using binary search. This is log n. That's good. Let's ruin it and let's just go linearly. So we're doing a linear search in both directions. So this is a bidirectional search, right? Until we find the first and the last. It's pretty simple. Makes sense. Do binary search because we know that's more efficient. Find the target, and then we're going to search left and right, and then we're going to just find it from there. However, what if you had this array? What would be your time complexity? So can someone answer? What would be your time complexity if we did this version of our algorithm?
Would it be O of n?
It'd be O of n. Why?
Because since all the numbers are the same and you're searching for the edges, you're gonna end up searching the whole array, which is n.
Exactly. Yeah. So we thought we were being smart by doing binary search, which yes, it is binary search. But if the whole array is 5, then all we're doing is we're gonna find this midpoint. We're gonna search through here, or we're gonna search through here, and in the end, we did this n times. So, what are you doing? What are you doing with your life? You're just doing linear search, but just more steps. So this is not the most efficient solution, but this is this would be a great solution to try out first. So if you're in an interview with with any company and they give you this problem, which this has been actually asked in, let me check. Facebook asked this question 11 times. Adobe has asked this question. Amazon has done this. Google, Apple, Bloomberg, Oracle, Microsoft, LinkedIn, Uber, Yahoo, TikTok. They have all asked this question according to Leetcode. So you're interviewing for these companies. They give you this question. You can give this as a solution because as it's better to have a solution than no solution. So this is a good first step. You try binary search. You're doing your best. You're giving it a good attempt, but the edge case of everything being 5s and your target is 5, it's going to be O of n. So in the end, this entire algorithm, even though it's going to be technically it's theta of log n, its average case is going to be log n, right? Big O of n, and big omega was which is best case, which you don't really care of 1, in case you find it in the middle. But actually no, log n. All right, let's do a better version. So let's erase all of this. Here's where we can get pretty smart. So this is actually probably the harder one of the two, depending on just because of this more advanced solution. But I think it's a pretty interesting solution. So here's what we're gonna do. We're gonna make a binary search function. We're gonna write it. So I'm not gonna write it because you've written this 2,000 times already. Okay? We're gonna make this binary search function. All right, and we're gonna give it an input, okay, of the array nums, target, and we're gonna give a boolean find first. Okay, this is a bool, true or false. What this is gonna do is we're gonna have a helper function where we're gonna search 2 times. So we're gonna do this. We're gonna call this twice. So what we're gonna do is binary search. So we're gonna call this just BS first, right? And we're gonna do so it's gonna be start first number, or I guess first, right? Start whatever first. I'll explain it. First is equal to binary search first, and then last is equal to binary search false, right? So what we're gonna do is we're gonna create a binary search function, and we're gonna find the first number of this list, right? The first instance of this 5, for example, in just one binary search. And we're gonna have a boolean just to have that set. So and then the second run through, we're gonna run binary search again, and we're gonna find the last number of that array. There's gonna be 2 binary searches, which means our time complexity is gonna be log of n times 2 log n. But since we drop constants, it's just log of n. The way this is gonna work is pretty simple. So say we're searching through this array. Again, we're gonna go through the one right here, okay? Say we're searching through this array, we want to find the first. All right, we did binary search. What that means that if we're trying to find the search, right? We're trying to find the first one, and so we found a target, right? Here's a target, 5. This is the midpoint. do this over here. This is our mid, 5 right here, mid. So if we're finding the first one, right, we're gonna just keep searching the left. So we found this number, it exists. So now we're gonna search the left part of the array. We're gonna turn this into mid, sorry, into high, and then we're gonna do binary search over here, which means we'll search here, and then it's gonna be here, and then we found this 5. Okay? So now we found the first number. Next is we're gonna binary search again with the same function, and here's the mid, right? Mid's over here, and now we're gonna find the last number of the array. So then we're just gonna, so if the target is equal to mid, right, then we're gonna search the right half of the array, because we know that it's either gonna be this number that we just talked about, right, or it could be somewhere later on in the array. So we're only gonna search the right half until binary search it until we find the last number. So we're doing 2 binary searches, finding left and finding right. All right. Hopefully this made sense. Let's code it up. All right, so here's a coding solution for finding the first and last position of the element. So like I mentioned before, we're going to create a helper function. So create a helper function called binary search. Okay. The function, I'm just going to comment it out. The function is going to search the left side of any target found until we get to the first. If find first is equal to true, else it will find the last, the right side, last instance of that integer. If find first is equal to false. So here's the definition. So here's a function, binary search. We're putting in the array nums. We're finding the target called target, and we're going to pass in a boolean called find first. It's either going to be true or false. Are we finding the first, or are we not finding the first? All right, then just left, right. If you've done this 100 times, guys, len numbers -1. Hopefully you're trying to memorize it. All right, result is going to store the index of the found target. So here's result. We're going to call it, it's going to equal to -1, because it says over here, if the target is not found, return -1. So we're just following the question. If you don't find it, it's just going to be -1 by default. All right. And now, while left is less than equal to right. Oh my God, I've done this like 100 times. Mid equals left plus right. Right and low plus whatever, low, high, whatever, same thing. If nums mid is equal to target, result is equal to mid. So we're just doing the same thing where we're trying to find the midpoint. And if the midpoint is the target, we're going to set the result to be that midpoint. So now, if we are looking for the first occurrence, we move the right pointer to the left of mid to continue searching left side of array. Else, we move the left pointer to the right of mid to search the right half. Right, just like we talked about. So this is where our boolean is going to come in handy. So we're still in this if condition. If find first, right equals mid -1. So we're just going to be searching the left half of the array. Else, left is equal to mid, whoopsie. Yeah, left equals to mid +1. All right. So if we're finding the first, search the left half. If we are not finding first, search the right half. And then just return the result, which is going to be -1 if we don't find it, or else it's going to be whatever. So this is our helper function, okay? This is just the helper function that we had. Now let's actually do the problem. All right, start. Our first number, right, is binary search. It's going to be nums target, and we're passing in true because we're going to find the first instance of it, so start, right? And then we're just going to say if start is equal to -1. So we don't find the first instance, right? If we don't find that target in our first pass through of the binary search, why are you going to keep trying again? Just return -1, -1, which is being a little bit more efficient. We're saying if we can't find it at all, what's the point of searching it 2 times? Because you're not going to find it the second time. All right. End is equal to binary search. Again, array numbers, target, and then just false because we're not finding the first anymore. And then just return start and end. I can't spell start. And if you run it, what did I do? Oh, whoopsie. I made a little typo. Wait, did I mess something up? Over 1 second, let me check. Time to see, hold on 1 sec. Left right equals 0, length numbers 1 is 1, result equals -1, while left is less than equal to right. Mid is equal to left plus right divided by 2. Result equals mid. If find first, else left is equal to mid. Oh, whoopsie, I forgot one part. So then we were here. So I forgot this one part. Else if nums mid is less than target, left is equal to mid plus 1. I forgot. Else right equals mid minus 1. So what I forgot to do was, so if we found a target, we're searching the left half, we're doing binary search over here. But if we haven't found the target in the middle of the midpoint, right, then we'll still have to do binary search. So we're just saying that if the current number is less than the target, then we're going to search the right half of the array, or else if it's less than the target, search the left half of the array, just binary search. So we should run this. Yep, we're good. Accepted. We passed the test. So again, just to summarize, we made a binary search function. We tried to find the first by just searching the left half of the array or else the right half of the array. We run that function twice. So our big O of 2 log n, which is simplified to big O of log of n in terms of time complexity. Any questions? Any questions at all? We're just doing binary search over and over again. No questions? I'm surprised. All right. If no questions, we'll do one more. This is a fun one. Let me take a screenshot of my iPad. And then I'll share my screen. All right, so here we go. Last round. Hope you guys are starting to really love binary search. All right, let me share my iPad. There we go. All right. Search a 2D matrix. If you guys took linear algebra, you might be getting a little bit of PTSD right now, so I'm sorry, because, you know, matrices are fun. All right. You are given an m by n integer matrix called matrix with the following 2 properties. Each row is sorted in non-decreasing order. Again, non-decreasing means it could be something like 1, 2, 2, 2, 3. You got dupes. That's why it's non-decreasing. The first integer of each row is greater than the last integer of the previous row. What's that saying? Is that over here, you see this 10 on this matrix. This is going to be always bigger than the 7 that we just pointed at. Likewise, this 20 is going to be less than the 23. All right, so that means that each row will be bigger than the last row. 100%. Okay. Given an integer target, return true if the target is in the matrix, or false otherwise. You must write a solution in big O of log m times n time complexity. Fun fact, I did something better. I did log of m plus log of n, which is less than m times n, so we're going to do my method instead because I think it's even better. All right, so what we're doing is we're switching to this matrix. What is a matrix in terms of programming? Like, well, how could you also describe it besides being a matrix, which you do in linear algebra? What data structure is this? Does anyone know?
An array of arrays.
Yeah, it's an array of arrays, a 2D array. So people who took CS 111, which is the intro CS class, you learn what a 2D array is. A matrix is just a 2D array. A 2D array. Don't tell Saeed Zakir I said that. All right, so we're going to be searching through a 2D array, and we're trying to find if this target is in this 2D array. So what can you do? Let me zoom up over here. Here's your matrix, right? This is your matrix over here. What we could do is we could search through targets. Let's say target is 3. Let's say target is 34 just because it's easier, right? We can go search here. No, 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 no. Oh, my guinea pig screaming. She's excited too. 34. We found it. Is this sufficient? No, that's called linear search. Stop doing that. That's bad. So if we did that, actually, our time complexity would be, for linear search, would be, oh my god, sorry for my guinea pig speed. It'd be O, big O of n, it'd be n times m. Because we have n rows and m columns, right? So the big O of n times m, that's bad. Don't do that. Don't make my guinea pig sad, because she's gonna cry. All right. Instead, we're gonna do binary search again. I'm pretty sure you guys figured that out already. Why? Because it's sorted. So if something is sorted and you're searching through an array, what algorithm should come into mind? Binary search. That's the most efficient search algorithm of all time, and it's so easy. So what we're gonna do, in a nutshell, is we're gonna do binary search. First, we're gonna search the outer rows, right? So we're gonna search the outer rows, right? And if the target is, say the target is, let's say the target is 16, right? And say if the target is between the first and the last digit of our current, so here's our midpoint, right? Our midpoint of our first binary search. If our target is in between these two, first and last, then it has to be in there, or it would be in there if it exists. So say if target was 17, you would still say it's between 10 and 20, so you're still gonna, so then it still might be in there, right? So once we binary search and find our mid row of the 2D array, because again, remember, Leetcode will give you like 1,000 rows and 1,000 columns, so you're still doing a lot of work. Then let's binary search it again. So binary search in binary search. All right, that's pretty much all we're gonna do. So again, to recap, we have a 2D array of matrix. We're gonna do binary search for each midpoint that we find. If the target is between the first and the last digit of this matrix, so you can do that in Python, you can check the first and last for in an O of 1 retrieval, then we're gonna binary search just that one specific array inside of the bigger array. So you're gonna be doing binary search, which would be log of m for rows plus log of n as your time complexity. Because you're only doing it one time, so it's m plus n, not m times n. So this is actually more efficient than the solution they give you on Leetcode. Any questions? My guinea pig has questions. I don't know if you can hear. Oh my god. All right, let's code this. Oh. I don't know if you guys can hear some incessant screaming. I think they hear me talking a lot. They're getting pretty excited. All right, so let's do binary search again. So first binary search. Searching the rows of the matrix, right? Low, high, get tired of this, equals 0. Length of numbers, oops, matrix, not numbers this time, -1. All right, guys, what's our next part of our binary search? What's our condition? What's our while loop? Can someone tell me? Please tell me you're paying attention.
while low is less or equal to high?
Yes. You can continue talking. What do we do next? What do we find next?
I guess the first thing that you can do is check if the middle is the value that you're looking for.
Yeah, we just find the mid. Cool. Thanks for answering, whoever you are. I appreciate you helping. Fred, you're here, right? Fred, you here? Freddie B? Oh, Carlos. Hi, Carlos. Fred.
Yeah,
Fred
I'm next.
Burke. Okay, cool. Fred, what do we do next?
We have the if statement.
Yeah. So now we found the midpoint. We want to search that midpoint. Is it? What do we do next? Come on, Fred. I just said it. Fine. Fred gives up. I'm
Yeah, we're
disappointed.
checking if the midpoint is in the array.
Kind of. Yeah. There you go. So we're gonna say if target is greater than the matrix mid 0. So what we're saying is the target, if the target is greater than the first number of our middle row. So we're switching the rows, right? If the target is greater than the first digit of the middle row, and the target is less than the last digit of that middle row. So we're indexing into that, right? So that's saying if our target is somewhere in between our row, our middle row, current mid. Low is equal to 0. Our target matrix is equal to mid. High is equal to length of matrix mid. And binary search the row. So we're just doing a nested binary search. So our first binary search was over here. If we found, we haven't done the full binary search yet. Actually, let me ignore this part. Actually, let me skip this part. Not this part yet. So the first outer binary search, sorry, let's continue that. So else if, so while else listed to go to high, else if, let me just actually do this all like lower over here so you don't see it. Else if target is greater than matrix mid -1. So what we're saying is, so if our target is greater than the last digit of our mid current row, right? So if we looked over here in this image, right, if you're saying the 10, 11, 16, 20, right? If our target is, say 30 in this array that we just, in the first picture, right? And we're looking at the midpoint, then we should search above this midpoint, the other matrices, the other rows, sorry. So it's going to be low is equal to mid plus 1. Else if target is less than matrix mid 0, so that means if it's less than 10 in the middle row over here, so it has to be in the upper rows, then high is equal to mid -1. Else if target, and here's an extra condition, right? Target is equal to matrix mid 0. So we're saying, just checking, just for fun, right? What if our target was 10 or 20? They're at the edges of the array. It's instant. We can search that immediately without even have to do anything. So why even bother, right? So if it's between 10 and 20, or target is equal to matrix last digit of the matrix of the row, return true, right? Does that make sense? So first binary search, checking to see if it's not between the current mid row, search left or search right, or just in case, is it the first or last digit of a middle row? This is a little base case to make it a little bit more efficient. All right. Now let me go back to the first part. All right. So we did those cases. Now we're going to do our nested binary search. So I'm going to add some more space so you can see. So while low is less than or equal to high. Yeah, we doing it again, boys. Well, like the matrix, but actual matrix. Mid is equal to getting deja vu, like Olivia Rodrigo right now. Divided by 2. If target is greater than matrix, target matrix, midpoint. So what we did, again, just to remind you, we set the mid to be, we called target matrix the mid, so you can technically call it target row, but whatever, call it target matrix. Low is equal to the mid plus 1. I've done this like 200 times. Also, target is less than matrix. Target matrix mid. So we're just doing binary search inside that row. High is equal to mid minus 1. Positive low is equal to high, and target is not equal to matrix. Target matrix mid. So we're saying if we have searched the entire row, right? If we search the entire row and our high and low is say both 11, and we haven't found 12 or something, right? Then it's not there. Return false. Or else return true. Skibbity bop. Easy peasy. And then again, where's it called? If we haven't returned anything, just return false just in case. That should be it. So we run it. Easy peasy lemon squeezy, we solved the problem. So it's accepted. So again, what we just did was we did binary search to find the correct row, and then we binary searched the row to find the correct target. Easy peasy. 2 binary searches. This would be, time complexity would be big O of log m plus log n, with m being rows, n being columns, which is more efficient than log m times n, which is what they asked you to do in Leetcode. All right, any questions?
Yeah, could you explain again how is this log of m plus log of n instead of n times m?
Because log m times n, which would mean that you're searching through each row and binary searching so each time you do a binary search, you do a binary search inside each row. So for example, say that we had a really big matrix, like say, was it over here, right? If we had like a bigger matrix, it would make more sense. But say we have over here, right? The first matrix, say our target is 3, right? And say our first mid row is 10 to 20. Log m times a would mean that for 10 to 20, we would binary search this anyways. Then we would go to our next one and find the first row and binary search it again. So you'd be doing binary search multiple times. So all we're doing is that we're being more efficient, and we're just trying to find the actual target of the row and then binary search that. Reason being is I think because in some languages you can't index the end of the array, so you might have to be a little bit more inefficient, like in C or something. But in Python, you can check like the last number of the, you can peek at the last number of the array. So we're skipping a few steps. Does that make sense?
Yeah, I think that makes sense. Thank you.
Yeah. So instead of doing multiple inner binary searches, you're just doing one. So you're doing one big binary search of the rows, and the second you find that column, you're searching that one column rather than searching multiple times the column. So you'd be searching each column each time, which is kind of a waste of time.
Okay,
Any
yeah,
other
that
questions?
makes
Yeah.
sense now. Thank you.
Yeah, because I think in C or something, or C++, you can't, like, see over here it says mid -1. The -1 is a Python thing. So -1 means the last index of the array. If you had a random array, you might not be able to search that. You might have to do something like, I don't know, like array.length, and then check something like that. But then it'd take a little extra few steps. Okay. Any other questions? No? Last chance. All right. Hopefully you guys all understand binary search now. I really, like I said, I always do recommend going onto Leetcode and doing lots of these same problems. There's a lot of cool binary search problems, and memorize it. Next week, we are going to be doing linked lists. So we're going to start doing some more abstract data structures. We're going to do linked lists next week, and then the week after that, we're going to be doing trees. So be ready for that. All right, guys, have a wonderful night. I'm going to go feed my guinea pigs. I'll see you all next Friday.
All right, later, Jorge.
Bye, Fred.
Bye.
Oh, it's Eric. Hi, Eric. Say hi to Kevin for me, Eric. All right, bye, guys.
Alright, peace, bro.
Bye bye.
Let me stop